All right, so Mr. Robs here today, and we're continuing linear regression part 2. And so in this scenario, we have the cake temperature, at different temperatures. It creates cakes of different heights. And we were able to determine from our GDC the line of best fit is this scenario, and here was our line here. And so now, so just to recap, I know in my lists I have all of the values placed, and it says use your GDC to find T bar, H bar. This means the average T, the average of all these temperatures, the average, and the average H value, okay? And then show that this point is on your regression line. So in order to do that, I'm going to go to Stat, and I'm going to calculate, and this time I'm going to do two variable statistics because these are two different variables as opposed to one variable with a frequency list, two variables. And my frequencies are just going to be blank because they all count for one value, and I'm going to calculate them. And so if I use good notation T bar and H bar, I know T bar is equal to 350, and my Y bar is 16.3. 16.3 is my average H value. And then what we want to do is show that this point is on the linear regression line. Well, one of the properties that I know about this line of best fit, this linear regression line that we use with our calculator, is this point will always, always, always be on the line of best fit. And it's approximately, if I look at my graph, it's approximately going to be at 350, 16.2. Okay? But we have to actually calculate it. So I'm going to take this value, and I know that H bar is going to have to be negative 0.0293 T, which is 350, plus 16, oh, not 16.3, 26.5667. And I know that in my calculator, I've already done the calculation when I did the regression and put it here. And if I trace that value, and if I trace it, change to Y1, I can go change the different scenarios. I'm going to do it at 350. And when I get that calculation, I do indeed get 16.3. And so I've shown that it is on the line of best fit. So we have this slope here. What does a slope mean in context? And to answer this question, we need to use the value, and we need to refer to both temperature and height to answer it correctly and very clearly. So what it means that and if I think about slope, in general, slope is like the change in y over the change in x. And the easiest way to do it is I'm always going to start with whatever the x variable is. And so what I'm going to say is as the temperature increases by 1 degree, and I'll always call it 1 degree, the height decreases by 0.0293 centimeters. So each degree of Fahrenheit that I set my temperature in the oven, the height of the cake will not get as high. It'll get 0.0293 centimeters less. So as the temperature increases by 1 degree, on average the height of the cake decreases by, I missed my B, by this. And so in doing this, note that I have talked about the temperature, I've used that variable, I've talked about the height, and I've used the actual value. It's decreased because it's a negative, and even better, this should be on average. I'm not saying every value exactly this does, on average it does. And that is a very clear, concise answer for what the slope means in context. The C value, now what does the y-intercept mean in context? Well, the y-intercept is when my x, my temperature, is 0. So if I look at that, this here is my y-intercept. And that means when the temperature is 0 degrees, that the Fahrenheit, when the temperature is 0 degrees Fahrenheit, the height of the cake is 26.5 centimeters, which we know makes no sense. So if I'm like, a temperature of 0 Fahrenheit is actually about negative 32 degrees Celsius, you're not going to get the cake to cook at all. So we know it makes no sense, but graphically and algebraically, that's what this would actually mean. That value would work. But in regression, we know oftentimes these extreme values like the y-intercept don't actually make logical sense. All right, so now we have our equation. We want to predict the height of the cake when the temperature is 3.2. So that means we want to find the height when the temperature is 330. Well, that's straightforward enough. So I know I have this. If I just type 330 into my equation, that's my x value. I plug it in and I get 16.9. So the height should be 16.9 centimeters. It's the three significant figures. And so I just plug the value in for t. Similarly, if I want to predict the temperature if the height is 18, well, if I put 18 on there, I want to find the corresponding height. So if I go to y equals, and I put 18 on here, okay, and then I graph this. While it's graphing, I'm trying to solve the equation. The height is 18, and it's negative 0.0293 t plus the 26.5667. And so the t is not shown on my graph yet because I have to change my window to make sure it includes 18. So if I go to my y maximum, I make it up, let's say 19, so I catch it. Now when I graph it, I'll see my line and I want to find the intersection of those two. And so I find the intersection and I get the temperature should be 292.5, which is approximately 293 degrees Fahrenheit. And so we just use our line equation to calculate the values. Then Bob's friend Sean baked a cake at 370. It rose to 15.5. Based upon the model, who would have the tallest cake? Well, let's try and see what the model will give at 370. So I want to find h at 370. So again, I'm going to go to my calculator. I'm going to trace at 370. And my model says the height is 15.731 to 3 decimal places. So who will have the tallest cake? Well, Bob will. Bob is taller cake. For bad English grammar, has the taller cake. And it's taller if you want to find the difference between those 15.73 minus the 15.5. I know it's taller by 0.23 if this model is accurate. Okay, so Bob's cake is taller. And finally, Bob's wife Diane wishes to use the model to predict the height of the cake when the temperature is 600 degrees Fahrenheit. Why is this a bad idea? Well, when we consider our graph here and our data set only goes from 300 to 400 degrees Fahrenheit. We cannot assume that the pattern will continue for higher degrees of Fahrenheit. In fact, I'm pretty sure it won't continue. Because if I go to 600 degrees Fahrenheit, that's 312 degrees. I'm going to basically incinerate my cake. And so it's a bad idea because, and the fancy word for this is the 600 is outside of our range. So this is extrapolation is the fancy word. Extrapolation. 600 is outside of our data range So it's not reasonable to assume the pattern continues. Pattern continues at these temperatures, at this high temp. All right, so it's a bad idea to extrapolate, and I'm basically going to incinerate. I'm going to incinerate my cake, and it's not going to have any height at all. All right, so at this point, there's our regression idea, and you're set to ready to practice.